Well, good evening, everybody. Welcome to the Texas Instruments Australia webinar series. In this webinar, Melissa Hirrigan from Brisbane in Queensland and Carol Mole from South Australia and Adelaide will be demonstrating how the TI-84 can be used in mathematical modelling. As a side note, the TI-84 colour edition will be available in September. Tonight's examples will include examples on statistics, functions and geometry. This webinar is being recorded and will be available on demand on the Texas Instruments Australia website. During the webinar, if you have any questions, move your cursor to the top of the floating icon of the desktop and you'll see that there is many commands you can actually ask and look at this chat and questions and answers. If you'd like to have any questions or questions to ask people, is to actually select chat and send a message to all panelists. And through the evening, we'll endeavour to answer as many questions as possible. And at the conclusion of the webinar, an email will be delivered within 48 hours of the conclusion of the webinar, and you'll see that there will be one for your webinar certificate. Now, our first presenter for the evening is Melissa Hirrigan, and she's a senior mathematics teacher at Narangba Valley State High School. And over to you, Melissa.
Thanks very much, Rodney. Just getting my PowerPoint going. So, as Rodney has said, we are looking tonight at mathematical modelling with our focus being on the TI-84 Plus. As I'm going through this, I am going to demonstrate a couple of activities tonight. I'm using the Smart View emulator for the TI-84 Plus. I have it in colour mode. Rodney also mentioned earlier that the CE, the new TI-84 CE, will be available in approximately September. That's the one with the rechargeable batteries, coloured screen, etc. We did a webinar on that earlier in the year. And the emulator for that is available for purchase as well. So just continuing through, as the program numbers used to always open, we all use math every day to predict weather, to tell a time, to handle money. But math is more than formulas or equations. It's logic, it's rationality, it's using your mind to solve the biggest mysteries we know. For students in classrooms, I don't think we can quite say the biggest mysteries we know, but certainly we need to be showing them how maths can be used and how maths is used to do so many of the everyday things that they may not realise involve mathematics. So in this webinar, we're looking at how we can use technology as a tool to assist us with teaching students the process of mathematical modelling. So what we're going to look at is, first of all, what is mathematical modelling? Because, as Rodney said, I'm from Queensland, so I work under the Queensland system, currently teaching Maths A, but also am a Maths B C teacher. So I'm going to look at how we look at mathematical modelling in the Queensland system under the Queensland syllabus, and Carol is going to be looking at how it's applied in South Australia. Really, you do any sort of research for mathematical modelling and the processes are the same. So I'm going to look at, first of all, at what is mathematical modelling and then go into the activities, looking at a couple of examples using the TI-84 Plus, and then Carol's going to do the same thing. So first of all, in preparing this, I wanted to make sure that I had a good understanding of what mathematical modelling is. And so you can do a lot of research. There's a lot of information out there. I work on mathematical modelling is, if you have a look what a model is, it's something that is made to look and or work like a specific object. So you think of model cars, they look the same as the actual car. If they're remote control or whatever, then they can drive and that sort of thing. So mathematical modelling, obviously, or it follows that mathematical modelling is applying a mathematical process to solve a problem. So it's going through, it's taking a real world problem and looking at what maths do we know, or what maths can we apply to solve that problem or to head towards a solution to that problem. And maths is used in so many different areas, and I think students get so used to just seeing textbook examples and being told, well, okay, the area of a rectangle is length times width, and let's now do 10 questions that are length times width applying the same thing. But we need to make the maths more real to them if we're going to prepare them for their life outside the classroom. So that's what the mathematical modelling process is about, getting them to look at where do they actually use this. Try to answer that question of when are we ever going to use this. So the modelling process, and this is a process that is used in a lot of industry and that sort of thing, and we need to make sure we're making students aware of that. So the modelling process begins up the top here, where we have some sort of problem. Now, I've called it there and I've put there real world, but obviously in a classroom, we need to make it's life related or similar to real world. We can't do everything in the real world situation. So from there, we need to teach the students how to change that problem into some form of mathematical problem. How can we look at it from a mathematical perspective? Something that students need a lot of developing with is the making of assumptions. And I know in the Queensland syllabus for Maths B and for Maths C is one of the assessment criteria is the effects of assumptions. So we need to get students to start to think about what would happen if this wasn't correct. We've assumed something, etc. And what actually happens then from there, they decide the assumptions they're going to be working with or what they can work with, develop their mathematical models. So in terms of calculations and that sort of thing, for models, we're looking at graphs, we're looking at equations, we're looking at diagrams, anything that can help them towards getting a solution. They then need to go and follow through that process, so draw the graph, read from the graph, whether it be develop an equation, whether it be look at a diagram and work through steps to use that diagram to solve, get to a solution, interpret that solution. Now that's something else that is in the senior maths here in Queensland, but it's something that from my experience students don't always do. They get to this stage of the solution or the answer and they stop there. So we need to remind students that in mathematical modelling you need to interpret that answer that you've got, link it back to what the original problem was, and quite often the process doesn't stop there. Perhaps the assumptions that we made were not good assumptions, or perhaps we need to consider the assumptions and how it might change. If we change one of our features, how is that going to change the solution that we've got? So you work through this process, and as you can see, it continues around. It can skip from the real-world problem back down to the assumptions here, go back through the model, and it can be an ongoing process. So students need to be shown that, and we really need to make sure they understand that process. So before I go in and look at some examples, just very quickly so that those of you who are not Queensland senior maths teachers can see where I'm coming from with my examples and my information here. In Queensland, we have for our senior maths the Maths A, Maths B and Maths C. Now Maths A is generally classed, or is your lower of the three OP level subjects, so university entrance subjects that students can do as such. Those students that want to study a higher level maths are looking at going into science, going into engineering, going into any of your higher level courses will generally do Maths B, and those students that, again, looking at engineering and things can then choose, if they're doing Maths B, to choose Maths C. What I've got here, this statement was taken from the Maths A syllabus that we're working from, and we actually have the criteria modelling and problem solving. And in that criteria, it talks about the students need to be able to interpret, clarify and analyse the problems. And I teach my students that that's about interpreting is taking out the information from the question or from the problem. And also it's about being able to transpose it, whether it be transpose it to, excuse me, a table or transpose it to a diagram or something like that. They need to be able to decide what strategies to model and solve. So what formulas have they got that they can use? Do they need to find the area? Do they need to find the volume? What sort of shape it is, etc. Investigate alternative solutions. Is there another way to do the problem? Is it a better way? Are there multiple calculations, etc. in there? Make decisions informed by the mathematical reasoning. So that's that process of going back and interpreting the information and then deciding, okay, from there, what decision can I make? And then reflect on the effectiveness of the model is one of our highest order ones in Maths A, and that is where they've got to look at the process that I followed. Was it an effective process? Do I need to rethink parts of it? So what are the strengths and the limitations, and how can I do that? What might I change if I was to do this style of question again? Maths B and Maths C have those same parts in it, but they also do have specifically criteria statements around effects of assumptions and what the decision on the assumptions, how does that change your decision-making process? So that's where I'm coming from a senior maths point of view. Now the other thing that I investigated too, because we have the Australian curriculum, and graphics calculators are definitely not just for year 11 and 12. My idea is to get them into the hands of all high school students, and I even actually use things such as the TI Inspire with primary school students at the moment as well, but getting the 84s into their hands as well to show them what can be done. So I looked at the ACARA, the mathematical modelling that's in our Australian curriculum P to 10 maths, and under the problem solving, which is one of the criteria, I guess you could say, its students develop the ability to make choices, interpret, formulate, model and investigate problem situations. So what we're looking at there is, again, that interpreting the information, so changing it from the real world problem into a diagram, a graph, statistical gathering, all that sort of thing. Go through the process, do the calculations, and then communicate the information effectively, so analyse it. So right down in the junior grades, they are doing some form of modelling. So we need to be making sure that we are using the technology to our advantage to assist the students in seeing how maths can be used. So enough of the background information. What I'm going to look at now is a type of problem that can be seen as a mathematical modelling problem. So instead of just saying find the volume of this box or find the volume of this rectangular prism, what we could ask the students from a basic level question is how much space is inside this box? And because we haven't said in the wording what is the volume, they need to understand that how much space is inside this box, it's asking them to find the volume. So they have to interpret the information, and from there they need to decide, well, it's a rectangular prism. How am I going to find the volume of my rectangular prism? So we're finding the volume of a prism, and we know that we have the length, we have the width, and we have the height with a rectangular prism. So therefore we can go and find the volume as area of the base multiplied by the height, or they might just say length times width times height. Now the interesting thing, that's a basic level question. That's something that definitely Year 8s, Year 9s can deal with that, and we need to teach them that to understand things such as how much space, well, volume is the amount of space occupied by a three-dimensional object. So, but it's linking something instead of just saying find the volume of this prism. My question though is, and we can pose this to students, if I just measure this particular box length, width and height, how accurate am I being in terms of being able to answer how much space is inside the box? And if we pose that to students, most students would probably look at it and go, well, depends on the accuracy with regards to using the ruler, etc. But what I'm more leading towards here is that we can pose the question to them, well, I'm asking how much space is inside the box, but my measurements there that I've indicated are the measurements on the outside of the box. So what we need to think about is, well, does it matter with our box there what the dimensions are inside the box? So in other words, what is the thickness of our cardboard? Because if I'm taking the measurements from the outside of the box and we've got joins there and that sort of thing, the dimensions for the inside of the box are going to be a little bit different. So this is where we can go down the track of saying, well, okay, what happens if we want to remove the thickness of the cardboard and really work out the volume of the inside of the box? Now, given the size of it, I don't think I can fit inside and use my ruler to measure inside. So I need to look at what's the thickness and remove that thickness of cardboard. Okay, so what we can look at there in terms of the modelling is that the length of our box is going to be length minus the thickness of the cardboard at each end. Using that same process, the width of my box is now the width minus the thickness of cardboard at each end. And of course my height is now my height on the outside minus the thickness of the cardboard top and bottom. So using that and my area of base times height, I now have length minus twice the cardboard width, width minus twice the cardboard, and height minus twice the cardboard, and I'm multiplying. So it's not quite as easy a question in terms of the calculations. So what can we do to investigate this further? And that's where we can bring in TI-84+. We could use something such as a cell sheet app to investigate how the volume changes with the change in thickness of the cardboard. So when you're using your TI-84, so I've got the Smart View emulator here. So I'm using my TI-84, it's in graph mode at the moment, but I can go into my apps, which I've just realised I've lost some of my apps and I don't have my cell sheet one in there. That's a bit of a bummer. I will just change. As you can see with the Smart View emulator, if you've downloaded the versions of it, you can actually switch back to the non-colour version. So just go back into my apps, and that's much nicer. I can see my cell sheet there. So if I choose cell sheet, and I press my any key, cell sheet is a spreadsheet, but on our calculator. So if you're not able to access computers, and I know that I have trouble getting access to computer rooms at school because they are as rare as hen's teeth and everybody wants to use them at various times. So we can do some spreadsheeting there, and you will see this slide here, or this screen here, the equals is how we store, or when we want to put, when you need to put equals in to write a formula, you press the store key. The RCL, as in the clear one, which is second function of store, is going to give you dollar signs, etc. So what I've got here is a spreadsheet which I prepared before, where if I had that my length was 50 centimetres, my width was 40 centimetres, and my height was 50 centimetres, I can then look at our volume. What I've done here, my D column, is actually looking at the thickness of my cardboard. So if my cardboard was 0.5 of a centimetre thick, I can then set up in there a formula, sorry, my formula, which is down in the formula box down the bottom here, that does the calculations, but it also subtracts out the thickness of my cardboard. So I've actually put the formula in, my length minus twice the cardboard multiplied by my width, etc. And the students can start to see that obviously what we'd expect as we increase the width of the cardboard, then what is happening is our volume is reducing. So that's one way to see it fairly easily and fairly quickly, and that's where spreadsheets come in very handy in the classroom. The Spell Sheet is an app that you're able to download, and students can download and put onto their 84s. So that's an option there. Now the other option that we can do is that we can investigate it using a graph. So this is another way of modelling it. So one way of modelling it is using a spreadsheet. Another way of modelling it is to use a graph. So I've put it in the form here where X is the width of my cardboard. Fingers crossed this is going to open up. Maybe not. So I'll just go back in there. So I'm going to quit out of my app, something that we need to remember to do. You'll see with the app that you've actually got, I had options down the bottom here, and so I'm using these keys as my function keys. I'm going to choose number 6 to clear out of that. And what I can then do, once I clear out, is I can go into y equals, and I can put in my function there. So I'm just going to put in my 50 minus 2x multiplied by 40 minus 2x multiplied by 50 minus 2x and hit enter. Now that is my function in there, remembering that I'm working on x is my width of my cardboard. What we always need to remind students of is when they are about to graph something, if we ask them to graph something by hand, they have to decide, they draw up their x and y axis, and they need to decide what scale am I going to use, what numbers do I need to use. So if I have a look at this, if my x is 0, I've got 50 times 40 times by 50. So in my mind, I should be working out the fact that, well, 50 times 40 is 2,000, and then times that by another 50. So my numbers are going to be up fairly high. If I go to my window, I'm not going to see anything if I plot my graph right now, because I've got my x values at negative 10 to 10, but my y values from negative 10 to 10 as well. So I need to alter my values. Now realistically my cardboard can't be negative 10 centimetres thick, so I'm going to change that one. I'm actually going to put it in as just negative 1 for the moment, because I always like to see my axes there. Okay, I'll leave that at 10, but I don't think I'm going to have 10 centimetre thick cardboard, but I'll leave it there so I can see my graph, and I'll leave my scale as 1. Now my y minimum. Y is my volume. Again, we need to discuss with students, and they need to be recognising and commenting on the fact that we don't end up with negative volumes, because measurements are not negative, so we can't have negative volumes. So the reason why I'm going to leave that in at the moment, though, is for the type of graph that we end up with, so that students can see the information, see the type of graph. So if we have a look at it, we've got negative 10, but I need to go to a maximum of, as I said before, say 100,000. So what I will actually do, I'm going to go from negative, I'll go from negative 10,000, only so that I end up with a nice scale. And I'm going to go up to, actually I'll go past 100,000. Okay, I'll go up to 1 million. And it's no good having a scale of 1. Again, we need to teach the students, if they were drawing this up, you're not going to put marks every one. So I'm going to actually work in a scale of 10,000. So now, fingers crossed, I get my graph. Now I've made a mistake in there. Again, I've got a graph, that's one good thing, but I've gone a little bit too far with my scale, so I can go back. Now what I can do, and this is where we can teach the students to use the likes of zoom in, zoom out. We can do a zoom fit, which fits our data on the screen, or we can do even a zoom in. With a zoom in, they need to decide where the center of the screen needs to be. Where are we zooming in towards? So I'm just going to move down, as you can see, just using my arrows there, to move down and across to see closer to my data. Except I always get this wrong. I needed to zoom out, not zoom in. I always mix those ones up, so I do apologize there with that. Just to make it a bit quicker, I will go down and just do zoom fit. So sorry, I should have zoomed out there. To get a better graph. That's better, that's what I wanted. But what we will see is that looks linear. And again, we can talk to the students, should it be linear? Well, if we go back to what our function was, we've got x times x times x, so we should have a cubic function there. But we can discuss about, with this particular situation, the fact that we're cutting it off at the positive values, so not allowing negative measurements for the thickness of the cardboard and negative measurements for the volume, then we're not going to see the whole graph. So that's an example there of how we can actually use a problem-solving situation. So the problem-solving situation being, what is the volume of or the amount of space that is inside our cardboard box, and from there we can turn it into a more detailed style question. And we've got a couple of different options. As I said, with cell sheet, we can use the graphing for it to see, and the students are able to trace on the graph. If we want to go higher level again, we can look at the fact that we put on some restrictions. So the box, instead of saying how much space is inside the box, we could look at the box must have a volume of 0.03 meters cubed. So now we're looking at, instead of being 50 centimeters, with it being 0.5 meters. Okay, and then if the cardboard costs 20 centimeters per square meter, what's the most economical size of box? So now we're also bringing in, with our restrictions and that it needs a square base, we're bringing in the fact that the cost for the cardboard is now looking at surface area. And this is where we can start looking at maximizing, maximization, minimization, optimization, that sort of thing, and what dimensions produce the volume that we want with the smaller surface area and satisfying that we've got a square base. So you'd need to set it up, your lengths and widths are the same. So in this case, you'd be looking at X for your width, X for your length, your height can stay as H, but you've got it then equal to 0.03 and you're rearranging there. So those are the types of questions that we're able to do. Something else very quickly that you can do as well is to use, again looking at the apps, is you can use something such as Cabri Junior and have the student drawing up shapes and measuring, so they can draw up shapes in Cabri Junior and they can investigate the perimeter versus area situation. So if I've got so much fencing, what's the biggest area that I can have? And again, the modelling process of what do we need to find, how can we go about doing it, and working from there. So that's what I wanted to look at tonight. So I'm going to hand this now over to
Melissa.
Carol.
Thank you for that. Now, as Melissa showed you, it was very easy to see that it could toggle easily between the versions of the TI-84, and you could see that we could look at the different applications that we have. And personally, I'll never look at cardboard boxes in the same way again, Melissa.
Thanks, Rodney.
And it just reinforces the fact that mathematics is everywhere. From a simple cardboard box, we can go from volume questions to calculations of costs, and then optimization questions. Now the next presenter is Carol Mole. She's retired from the classroom. She works as pre-service teachers at Adelaide University, and she's a part-time role at the Maths Association of South Australia. And after all that, she's got some spare time she spends with her 5 grandchildren. So over to you, Carol.
Thanks, Rodney. Yes, I don't quite know how we fit all that in, but never mind, we do. So I'm going to do something a little bit different from Melissa tonight. I've put up a couple of little points on my PowerPoint. One of the things that I'm really concerned about is this sort of statement: weapons of mass destruction are calculators killing our ability to work it out in our head. A lot of people still have this funny belief that calculators are a way of cheating, and I think that's ridiculous. It's something we have to work very carefully to overcome. And so you've got control over this in your own classroom, and it's very important that you actually indicate to kids that the calculators are, in fact, an amazing tool for conceptual development. And I think that's the way we've just seen with what Melissa was doing, and I hope I'll show you some other ways with what I've got. I didn't worry about going through the ACARA statements and things, knowing that Melissa was doing that, but a couple of points about modelling as a mathematical practice. If you have students who are proficient mathematically, they can apply the maths they know to problem situations. They can make assumptions and approximations to simplify a situation. That's a very important one. You don't try and take in all the complexities until you have had a bit of a look at a problem, and revise later if you need to. Identify quantities, map relationships, etc., etc. Analyse what you get. Interpret your results, very important, and reflect on whether they make sense. Now, I've got a little example here called Fishy Business that will be available for download for you. It's actually rather a silly little activity. I wanted to find something that I could use the calculator for, and so I actually made up this little exercise called Fishy Business. So it's a bit of a fishy activity to do. I think that if you're interested in using this as an activity for your kids, you might find a better application than this one. But the idea here is that, totally unrealistically, the owner of a fish aquarium business has a population of 200 adult fish in a tank that can take up to 300. Any offspring are removed, so there's no problem with numbers multiplying inside the tank. In terms of marketing, he's not sure whether to aim to sell 20% of his stock or to ensure that he sells or actually takes out exactly 20 fish per month. You know, as you'll see, that's quite ridiculous. But anyway, after how many months will he have less than 50 fish left with each method? Now, this gives me an opportunity to use the calculator, of course, and just ensure that everyone knows how to use the iterative procedure with your calculator. So what I've done is say he's got 200 fish in there, first of all, and then he's going to subtract 20 fish per month and see what we get. Now, I'm sure you all know how to do this, but it's interesting to see how children actually use this. And, of course, if we keep on entering, the fish number steadily comes down. And so, in fact, we can see that by just subtracting 20 fish each month, eventually he is going to run out of fish and move into the negatives, if that was possible. By the second method, of course, put in our 200. Now, we're going to have to do 200 minus 20% of the answer, second. Where are you, answer? There. So I want to work out this 200 minus 20% of the answer. So, of course, that's actually 0.8 of the answer. So I'm going to just do multiplied by 0.8. I guess that little step is important because not all children know that reducing something by 20% means you're multiplying by 0.8. And again, we press enter and it will continue to come down. And this time, of course, the numbers don't reduce quite as quickly as the number where you took 20 off each month. And so you, in actual fact, theoretically, will never run out of fish because you'll always have 20% left to take out of whatever was left. Now, that's a bit unrealistic, of course, but after how many months, Part B, would he have exactly the same number left with each method? Now, the kids are going to have to go and have a look at those two screens again, and I'm not going to bore you with doing that, but they can actually do that, or they can have saved the information in a table. So I've actually done that. I've actually taken the two lots of data and put them in my table to see what was actually going on. And so we can see that with the second method, when the first method runs out totally after 10 months, there are still 21 fish left in by this other method. And of course we can graph that. If I go to second y equals, you'll notice I've turned on plot 1 and plot 2, and I'll just graph both of those. And we can see that one of these is a linear model, the other is an exponential model. I think that's one of the hardest things about modelling for our students, to understand the difference between linear models and exponential models and power models and so on. And in South Australia, there's quite a big section of work in our Year 11 courses on the various types of modelling fits to data. Now, I think this can be started at quite a younger age. So as soon as kids have a graphics calculator, or even if they don't, they could still be playing with this sort of exercise, and that's why I believe this is really important for them. And then what method of marketing would be most sensible and why? Well, the only sensible one is to reduce by a percentage each month. In this first question, of course, you would want to spend time with your students developing a formula for the model. And linear functions aren't too hard to work with, and exponential functions are a little bit harder. But if I go to y equals, I've actually written these in already. The linear function is 200 minus 20 lots of the months, and the exponential function is 200 multiplied by 0.8 to the power of x. And I had these turned off, so I'll now turn them on and graph that over the top of the scatter plots. And of course, we can now answer part B of these two questions quite exactly. After how many months would he have exactly the same number left with each method? Which method was the most sensible? Well, okay, we won't deal with that anymore. Suppose that the fish proves very popular and he decides that he will sell only 20% per month, but also to keep his stock up, he will introduce another 12 adult fish each month. Now, this first question is what is really important for your students. You want them to predict what they think will happen to this fish population. They will have watched the 20% coming down quite rapidly on the first bit. And if we only put another 12 in, what is actually going to happen? And students find it really interesting that this population actually stabilises quite well. So I'll just go back to the calculator, clear that screen. What I'm going to do this time is put in my 200, and now I'm going to multiply that 200 by 0.8, which will reduce the number of fish by 20%, which theoretically I've sold. And then I'm going to add on another 12 adult fish each month, and we see what happens. Well, it's gone from 200 down to 180, which doesn't seem right to me. So I multiply by 0.8, no, that was 160, of course, and add on my 12, I've got 172. And if I keep entering, something very interesting happens. We actually find that the numbers go down and down and down and down, but eventually starts to slow down and we think, well, hang on, it's not slowing very much now. It looks like it's creating some sort of stabilisation in the population. So it looks as though I'm going to get to about 60 odd fish in this tank. So that if I always sell 20% but add another 12 back in there, I will end up with a stable population of 60, which of course probably isn't enough to make it what it's doing. So we can repeat that with 30 fish added each month. And this information should be recorded in a table, then added to lists on the calculator so you can get a scatter plot of that information and so forth. Now, to save some time, how many fish should be added each month so that the owner has a stable population of 250 fish available for sale? In actual fact, what you need to do at this stage, and I'm going to see if I can make this work, you want to have a population, whoops, I've got to tell it to start inking. At this stage, I can say I want a population of fish. These are very wobbly things to use, so I apologise for that in advance. I'm going to have to say I want the population multiplied by 0.8 plus something like, let's say, 50. So if I add on 50, I'm not quite sure what's going on with this mouse, but that'll do. I actually need to solve something like that. So I want the population to stay the same when I multiply by 0.8 and maybe add on 50. And so I'm actually going to solve 0.2 lots of the population, terrible writing here, equals 50. And so when you solve that, you get P equals 250. So it's interesting that if you start with 200 and you reduce by 20% each month, but add an additional 50 in, you actually end up with 250 as a stable population of fish. So it's quite a neat little exercise for the kids to do, playing on their calculator screen to just see what's going on. Now, if you look at part F, this one's a little bit harder, and I'd like you to try that yourselves eventually, but what you actually have to do is, if you find that you start with 200 fish, take off 20%, and then add on perhaps another 20 or so, you will, or perhaps add on 50, as I did here, you will end up with 250 fish in your stable population. But it takes more than 6 months. So you've got to have a bit of a play with that. And what you need to do, in fact, is add on more than 50 to start with, so your population goes over 250, and then change what you're adding into something a bit less than 50. So it's really quite a neat little exercise to mess around with. I'd be very interested in anyone's views or a better application of this actual exercise. It was just the best I could come up with for the moment. Rodney, I don't know if anyone's got any questions about that at this stage.
No, only one question was during the night so far was talking about restricted domains. A participant actually talked about another thing in the modelling situation about restricted domains, and which is quite good with her situation with the box. And also, could you actually evaluate your home screen? So if you've got a function in Y1, could you evaluate what Y1 is on the home screen? Could you demonstrate that? So,
you want me to do that while I'm at it?
Yeah, if you've got your functions there.
I've got my Y equals in here. What I'm going to do is, just in case you don't know this, go up and turn off those statistical plots as well.
Yes,
so if they're highlighted in black at the top of your screen, it means they're going to come on if you graph anything. But anyway, let's come down to number, well, I might just turn off Y1 there, not that it really matters, but I'll go back to the home screen now, and what Rodney's asking me to do is look at Y2, say, evaluated at 50, say, and that's what comes out. And so you can take, because of this setup, you can actually pick any of the functions that you've got recorded in the Y equals, and you can evaluate them at any value that you like.
That's well done, Carol.
We probably need to make sure as well that we remind teachers to remind their students to check they've got the most up-to-date version of operating system in their calculators, because what Carol was just showing us there with the alpha is making sure those function keys are available with that operating system 2.55 MP in the TI-84 Plus.
With 2.53 as well.
That's true. Yeah, and also, Carol, sorry to interrupt, Carol, also your vars key, you could do it that way as well, but I'll let you continue.
So we just go to no. I just want, let me get out of that, come back to here.
Yep.
One thing, don't say up. The one thing I like about this calculator, you don't have to go in and out of menus like you do with a Casio. That's a little hint to buy TI. But you can do it with the vars button, and you have to go to vars, which is here, across to Y variables, and of course you can do it, as you see, with functions, parametric and polar, but I want it with this one, so I'm going to come down to number 2 and enter that, and I have Y2 at 50 again, so, or at 21 or whatever I might want to plug in. The other good thing with this newer operating system is that if I want to change the value, I can scroll up and grab it again. And because the cursor's on this line, I can now change that number to 25 if I like and re-enter that as well. So anytime I want to try a few values, I go up and grab it and down it comes. And because the cursor's on that line, you're still live. Does that answer the question there, Rodney?
That certainly does, Carol. Thank you very much for that.
And I think just going back to Melissa's exercise, if you've got a box with 50 minus 2x and 40 minus 2x, etc., it is a good idea for students to look at a limited domain for the values that x can take, because you don't want your volumes to be negative, and I think that's a really important point. Okay.
I think that definitely comes in where you've mentioned there, and as you've got on the screen, Carol, about interpreting the mathematical results in context and deciding do they make sense. And that's what we need to be teaching a lot of the students to be doing. I know myself that there's a lot of students, they will just take whatever answer the calculator gives them without looking at, is it realistic? So it's definitely working through that modelling process.
Yep. Exactly. Now, this other one that I'm just going to do fairly quickly because we're starting to run out of time. It's an exercise I've taken from a textbook that I got some years ago. I think it's a Victorian textbook, and I didn't record my source, so I apologise to whoever owns this problem. But this is a fish farming business. That was the reason why I made up the other silly one to go with that. But what this is about, it is your task to advise the fishermen of the best time to harvest. If you put little fingerlings in a pond of some sort, lets them grow. As time passes, some die, etc., taken by birds, and they get heavier and so forth. But he wants to be able to harvest the maximum weight of fish. And so there's a whole lot of information given in this exercise. You'll find that in the downloads that you will get from TI, this exercise is all totally written out for you with the screen dumps and so on for the calculator to go with it. So I can go through this reasonably quickly. So this information is known about fish lengths, weights and lengths of life. So for fish lengths, we know that as time passes up to 70 months, the length of this particular fish is heading towards something over 70. And so the first question is find a power model to fit this data. Now I've actually got the, I have to go up to File and I need to put that one in. I don't want to save the other one. So what this should have done now is actually give me that data. So I've actually got this data already in here. You notice that with the emulator, you can in fact save the emulator state. You give it a name and you can go back and reload that whole state. So you don't have to type in all your other information as I would have had to do to change over from the other problem. So what I have here is that I need to turn on, I've got that. I want to actually have a plot of this first, don't I? So I've got list 1 and list 2. I want to turn this guy off. Go back to this one. Turn plot number 1 on. And I'm just going to do, in this case, I'll do quickly a zoom 9. And there's my data for the weights of the fish. Now, it looks as though a power model suits this all right, so I'm going to calculate. go, sooner or later, to a power regression for it. This one lists 2, and of course you can store it in there, but I won't do that at the moment for a very good reason, because I'll ask it to calculate and I'll get an error statement. I think it's really important that the students actually see that, because most of the regression equations that are calculated actually try and change your data to a linear one so they can put a linear fit to it, and they use logarithms. And so we cannot actually have the zeros in our list of data because the log of 0 isn't going to work. So I go back to my list and I delete that one, and across to this one, and I delete that one. And now I don't have the zeros in there. I will now calculate. I've forgotten the number, whatever number it was. I should have remembered. Far easier than scrolling down. My power regression this time, list 1, list 2, and of course I can store it in a particular spot. I can use the bars button again, or I can just go to alpha Y1 if you like. So I'll put it in Y1, and whoops, doesn't like that, so I don't know what happened there. What don't you like about that? So there must have been something in Y1 already.
It's that one of your columns has got an extra data piece by the looks of it.
So let's have a, oh, that didn't go. So that's 0 that I was supposed to be taking out. Yeah, okay. So calculate, whoops. That calculate. I still forgot the number.
A, yep. Okay, here we go for A. Scroll down again. Alpha Y1 will do. Calculate, and we're in business. And I have a model that fits my graph, my data, and it should have pasted itself into Y1. And if I now graph, it actually graphs over the top of my model, and it looks like it's a reasonable fit. Well, perhaps it actually doesn't look like it's a reasonable fit. And this is one of the things students need to look at. If you get a pattern of residuals, and these are still called residuals even though they're around a curved graph, there is a clear pattern to my data here that is not modelled by my functional model. So I think it's not actually a very good model, because the power one's going to keep on going upwards, where we know that the data we had seemed to be levelling out at 75. And so I explain that in there, in this little sheet. We'll go to the next sheet. Given that it's also known that the maximum length that this species ever reaches is 75, to explain why this model is not particularly suitable. Well, the model drawn over the scatter plots shows a regular pattern, so the model's not very good. This model of the power function will grow without constraint rather than approach 75 as a sort of asymptote. This can get to this size, but will probably be harvested before reaching it. So it's really not an asymptote properly, but it will be when we try and put it in this sort of form. So as time passes, the length is going to approach 75, and a better model would be of that form. So we really want to have a look at the difference between the 75 and some sort of exponential model. So what I'm going to do now is go to my stat edit again, and over into column 3 here, I'm going to put in 75, take away list 2. Question, Rodney? We're okay?
Yep, you're good.
Okay. So what I've done is now find the difference between 75 and that, and I'm now going to graph. Turn this guy off for the moment. Come down, goes back and up, up, up. Come on, up you go. Cross to number 2, turn him on. And this time I want list 1 and list 3, and I'll just zoom 9 on that. Now, I now have my data looking like that. This line up here was the y equals that I had here, which I will now turn off. So back to my graph, and I now have what is clearly an exponential decay model. So this time I'm going to calculate an exponential decay. Exponential regression. Calculate that for list 1, list 2, and I'll store that in number 2. Calculate, and away we go. And I now have a model which is in number 2. And if I graph that model,
should have been list 1 and list 3, Carol, because you've changed the data.
It was, and I did, didn't I?
Oh, you still had list 1, list 2.
That's this one.
Okay.
All on.
You plotted it when you did the regression. I think you still
Done
had
that.
list 1 and
now
list 2. So when you did your regression.
Yep. Did I leave number 2 in there?
You did, Carol, yes.
Okay. Okay, yeah, correct. So number 3. Down we come, store it in alpha y2. Something like that. Okay. Where we go, calculate. Now we should have it in y2. Yes, it's a different model this time. If I graph it, my exponential decay model seems to fit. Okay. So I've actually done that now, and we can now have a model in this form. We can say the L is equal to 75 minus that. So that actually is a model for the length of the fish at any time t, 75 minus 77.8 roughly with that. Now the fish weight, same sort of idea. We're going to run out very quickly. I think I won't be able to do any more of this much. I'll just show you these screens. The weight length data is tabulated. Find the most suitable model for this fitting regions for your choice. Use eligible independent variable, etc. And we get a model for that, which I can't put over here now in number Y3, but that's all right. So I get a model for my weight, and then I look at the length of life. As time goes on, the number of fish actually reduce. And don't forget to omit the 0 when you do it. It's actually exponential decay going on, we could say, and a regression equation fits that as well quite neatly. And using all that information above, how on earth do we calculate at what time we should harvest the fish so that we get maximum weight of fish? So that's a picture of a nice big barramundi that my husband would like to catch but hasn't yet. It's not my husband either, but it was just a picture. So to have a look at this question, you can look at this as I've done it when you get the downloads, but it's really nice that you can actually, having these 3 fit into your plots, you call Y1 for part A, Y2 for B, and Y3 for part C, you can actually store these in your list. So I had to put in new list 1, which were 5 monthly intervals. I've then said find Y2 calculated as the value of list 2, much the same as we were looking back before at Y1 of 50 and so on. You can actually put these into your list as well. You'll notice I put little quotation marks around that as well so that I can always see what my formula was, and then I plug them in. And then in list 3, I put Y3 of list 1. And so Y3 was finding at certain times what was going on with the variable Y3. And then finally, I said, well, list 3 multiplied by list 4, putting into list 5 will actually tell me the total weight of fish that I have. And then I plotted that, and out it came looking a bit like this. So there's somewhere about here where I actually have maximum weight of fish at about 25 months. Now, to do it using the formulae, I don't know if people know how to do this, but in Y4 down here, you'll notice I put calculate the function Y2 of Y1 multiplied by Y3, and that will give me exactly the same result as I had before, and it graphs beautifully over the top of the scatter plot. This was my scatter plot, this is my function plot going into here, and I can then find the maximum point, and it turns out it's about 23.8 months. Of course, the accuracy of that depends on the figures used in your model, and of course, I did it at 5 monthly intervals. You could actually do it far more accurately than that if you wanted. Now, I hope that that's a little bit different from what Melissa did, but that's just a way of using a pile of data and having a look at it in terms of what you can get from these figures. Can you fit models to them? What can you do with them? And how do we get an answer to our problem? That in this case, at about 24 months, you'd get the maximum weight of your fish. And so that's about what I needed to say, and I just wanted to finish with this lovely little slide which says that the surest path to positive academic self-esteem is to succeed at something which one perceived will be difficult. And I think when we steal the struggle from students, we actually steal their opportunity to build self-confidence. And they have to learn to do hard things to actually feel good about themselves. We don't have to make life easy all the time. So thank you very much for that, Rodney, and we'll see if anyone has any questions of that.
Yeah, just checking the question. No further questions to that. So thank you to our wonderful modelers, Melissa and Carol, for their presentations. They're very informative. I picked up a lot of hints tonight and a few features of the T84 I haven't used for a while. And with the Texas Instruments Australia website, if you actually head to education.to.com, the Australian website, you'll see that you can either go through the teacher section, but you can actually click on the webinar link here, and in this section when it comes up, it actually has the upcoming webinars. So to whet your appetite, let's have a look what we've got coming up with the Australian webinar series. We've just finished tonight's mathematical modelling with the TI-84 family, and we have, on September the 1st, we have Harley and Peter presenting on exam readiness for mathematical methods, and there's quite a few around September, so readiness for the students for exams. In addition to that, if you move your cursor over to the on-demand, and with all the previous webinars that the trainers and other people have provided over the last few years, you'll see that you can actually watch the webinar online, or you can download it and save it to your external hard drives. I know I do that. I save the webinar so I can view it at any time, and any TNS files, PDFs, Word documents are all there as well. And you see how many there are if I just grab this and move down the screen. A lot of webinars this year, STEM, another one in 84, NAPLAN. So thank you for listening and watching tonight, and until next time, take care, and we'll show some webinars in the future. Bye for now. Thank you, Carol. Thank you, Melissa.
Thanks, Rodney. Thanks, Carol.
Thank you. Bye.